So, what is cappenin this week? Sesame farmers enjoy newfound knowledge courtesy of daring drone imaging. Nemetschek-out this collaborative remedy for housing shortages in Iowa. New MIT tech gives robots special vision, and industries are keeping tabs. LiDAR and 3D modeling eagle on golf course design, and a St. Louis AEC Error of the Week that was a convergence of racism, neglect, and corner cutting. Set that alarm for 4 a.m. and don't stop till supper time, recappers. We're off to the farm today for a drone imaging story blooming optimism for one of humankind's most cherished seeds. Hint, they're staples of burger buns and Asian cuisine. It took tireless work that was deeply intentional, quite unlike the happy accident decades ago that spawned the Agri-Drone, not to mention the subsequent mapping, monitoring, imaging, modeling, predicting, and by golly, smarter farming. Folks, gather round for the tale of the Yamaha R50. In the early 1980s, Japan's rice farming industry faced a significant labor shortage, exacerbated by regulations on manned crop dusting due to rapid urban expansion. Recognizing the urgent need for a solution, the Japanese Ministry of Agriculture, Forestry, and Fisheries approached Yamaha, a company renowned for its motorcycles and snowmobiles, with the unique request: create an unmanned helicopter to help farmers spray crops efficiently and safely. The commission was officially called RCAS, that's Remote Control Aerial Spraying System. And you bet your RCAS Yamaha was up to snuff. Engineers initially experimented with adapting snowmobile engines and complex counter-rotating rotor systems. But these early prototypes were beset by issues related to weight, cost, and stability, leading many to doubt whether the project was even feasible. But Team Yamaha remained undeterred. They pivoted to a more conventional design, utilizing a single main rotor and a tail rotor, much like standard choppers. This crucial design shift paid off, and by June '86, the first prototype was a wrap. In '87, Yamaha introduced the R50 Aero robot, marking a true denouement in early unmanned aerialism. The R50 was put to the test during a demo flight sponsored by the Agriculture, Forestry, and Fishery Aviation Association. It performed like a samurai on an HGH stack, crop dusting with a 20-kilogram payload. Yamaha initially produced only 20 units, distributing them to select farmers and closely monitoring their use, which quickly proved miraculous for spraying rice paddies, orchards, even golf courses. This reduced physical labor, but more profoundly, ingratiated the industry to younger farmers. By addressing the challenges posed by Japan's aging farming population, the R50 paved the way for the widespread adoption of UAVs in agriculture. In the early 1990s, the Japanese government established training guidelines for the R50, and the technology was soon being taught in agricultural schools and adopted by commercial farms nationwide. Yamaha continued to build on this success, introducing advanced models like the R-Max, which boasted autonomous navigation and greater payload capacity. These innovations not only influenced drone development in Japan, but also inspired similar advancements around the world, with applications extending to disaster response and environmental monitoring. The evolution toward imaging, mapping, and 3D came with later generations of Yamaha's unmanned helicopters, which have since been equipped with GPS, cameras, and even LiDAR for mapping and surveying, particularly in forestry and environmental monitoring. These augmented high-res topographical mapping and digital imaging with baffling finesse. Yamaha's R50 was not originally intended to revolutionize agriculture, but through one government commission, one pivot, and one prototype, we learned the sky wasn't the limit for farming. It was the solution. And as we'll cover shortly, it still is. Hit those show notes for some quick caps on Gaussian splatting Britain's busiest rail station, why your GIS skills are more relevant than ever, how photogrammetric mapping of an ancient temple in Bolivia shed light on a lost society, drone news galore, HP teams with Creaform to launch a 3D scanner, and are you still waiting for that personal humanoid robot? Because it's coming. Without further ado, recap number 1, Open Sesame, how drone imaging just conquered an age-old farmer's foe. Sesame is legendary. It's the oldest known oilseed crop, domesticated almost 3 millennia ago. It's the first known oil to be consumed by humans, and it's a great street. But it's not resting on its laurels. Demand for the oil has actually increased in the 21st century, what with its abundance of protein and antioxidants and surprising climatic resilience. But monitoring their health and classifying the types of stressors has been a permanent thorn in the side of farmers. Not helping matters is Sesame's abnormally high need for water and fertilizer. But a triple-camera aerial Sherlock Holmes of sesame fields has just harvested some novel intelligence in sesame farming, and the ISPRS Journal of Photogrammetry and Remote Sensing just featured it. The 3-cam drone sprouted from a team led by Dr. Itai Herman of the Hebrew University of Jerusalem, who aligned with Virginia State University, the University of Tokyo, and the Volcani Institute. The drone's camera trio that's getting seedy with it? Hyperspectral, thermal, and good old RGB. But the real magic is arguably AI that can spot when your sesame plants are thirsty and hungry, that's suffering from water and nitrogen deficiencies. This one's a biggie because traditional crop monitoring is about as good at multitasking as Joey Chestnut is in the middle of his 28th Nathan's Famous. It struggles to tell if plants are suffering from one problem, let alone two. But this drone-powered AI field approach boosted stress detection accuracy from a ho-hum 40 to 55% to a whopping 65 to 90. That means farmers can give their crops exactly what they need when they need it, saving water and fertilizer. Quote, by integrating data from multiple UAV imaging sources and training deep learning models to analyze it, we can now distinguish between stress factors that were previously challenging to tell apart, said Dr. Herman. The team tested this at the experimental farm in Rehovot, Israel, using a variety of irrigation and fertilizer tricks on sesame plants. The result? Early stress detection, better yields, and a shot at more sustainable, climate-friendly farming. So next time you sprinkle some sesame seeds on your bagel, thank the drones and the scientists, ensuring those seeds are smarter, stronger, and a little less stressed out. Recap number 2. Prairie Home Companions, an Iowa college and the Nemetschek group battle the housing shortage. In the long view, Iowa has fared well in this saga of exploding housing costs. But compress the timeline to the last few years, and the state's home costs are ballooning like the frequency of confusion with Idaho. It's the impetus for the Nemetschek group joining forces with Iowa State University. The aim is tackling the Hawkeye State's affordable housing shortage through digital twins, 3D printing, and a fleet of other tech that collectively form the Iowa Innovative Housing Project. As relayed by AEC Magazine, IIHP minimizes construction risks, slashes material waste, and delivers housing that's economically viable, environmentally sound, and sturdy as all get out. The current pilot phase sees the university leveraging Nemetschek's D-Twin solution to create an immersive digital construction environment. Through digital twins of each proposed structure, complete with copious dashboard analytics, the team can monitor and analyze building performance with utmost precision. The project will continue with the construction of a 3D printed shed that's more sensor-laden than a paranoid home security enthusiast's front porch, reporting on everything from air quality to energy consumption in real time. Quote, Nemetschek's D-Twin solution has changed how we approach every new home in this project, says Pete Evans, assistant professor of industrial design at Iowa State. Quote, we're able to visualize every aspect of a planned structure in one seamless view. We can monitor air quality and energy consumption and compare this with buildings constructed traditionally, giving us incredibly valuable insights. We hope to use the D-Twin platform extensively across every stage, design, construction, and property management, as we work to solve rural housing issues in an affordable and sustainable way. Go Cyclones! Just, not into homes or anything. That'd be excessive. Recap number 3. Kick rocks, Marvel. Robots see through walls thanks to new MIT leap. Mission Impossible's Ethan Hunt would require sci-fi special spectacles to see through walls. And all these robots need is some decent Wi-Fi. Yeah, MIT researchers have trained robots to peer through solid walls using nothing more than Wi-Fi signals. Dubbed MM-Norm, the breakthrough transforms ordinary millimeter wave technology into a sophisticated X-ray vision system that can reconstruct hidden objects with startling precision, and industries are at full attention. The researchers harness something called specularity, essentially reading the geometric fingerprints that waves leave after bouncing off surfaces. Quote, relying on specularity, our idea is to try to estimate not just the location of a reflection in the environment, but also the direction of the surface at that point, explains lead researcher Laura Dodds. MM-Norm achieved a 96% reconstruction accuracy on common objects with complex shapes, such as utensils or power tools, demolishing the previous state-of-the-art accuracy of 78%. It's a paradigm shift that could transform warehouses and give security systems superhero vision. And holy points for practicality. See, because the tech doesn't demand exotic hardware or massive bandwidth increases. It simply reimagines how we interpret signals that already surround us, turning ambient Wi-Fi infrastructure into a ubiquitous imaging network. Quote, "We needed to come up with a very different way of using these signals than what has been used for more than half a century," notes senior researcher Fadel Adib. So the route to the future is a route. Who'd have thunk it? Recap number 4. Tech's tea time. Golf course modeling and twinning for enhanced player flow. Golf course design has always derived from experience, intuition, and hopefully once or twice, bro, just imagine if we put the bunker here and the flag there, from a guy dressed like he was a property manager for Queen Elizabeth. But that's over, as one of 3D's more recent forays is landing on the fairway. The focal point is known as player flow, the sequencing of a player's likely movement throughout their round, and it is a green jacket of innovation, as relayed by the art section of Vocal.media. 3D scanning, drone capture, modeling, and digital twins are permitting architects to create digital replicas of landscapes before a single blade of grass is disturbed, and they're as accurate as peak Tiger Woods with binoculars. The tools of View My Golf enable designers to simulate how players will move through the course, identify potential bottlenecks, and optimize the sequencing of holes for challenge and enjoyment. By analyzing everything from terrain elevation to sunlight patterns, layouts can be fine-tuned to minimize wait times and maximize the natural rhythm of play. Every element, tee boxes, greens, bunkers, water hazards, yardage, and cart paths is positioned exactly as it exists or is planned, enabling a true-to-life simulation of the player's journey. The resulting courses are beautiful, while the golfer experience is delightful. In a sport where pacing and flow are crucial to enjoyment, digital modeling ensures that the design makes every round feel thoughtfully orchestrated rather than haphazardly assembled, of course by a guy dressed like he was a property manager for Queen Elizabeth. It's that time, folks. Your AEC Error of the Week. St. Louis's Pruitt-Igoe housing project was conceived as a bold experiment in modernist architecture and urban planning, but its legacy is one of rapid decline and eventual demolition, driven by deep-seated failures. From its inception in the mid-1950s, the project was plagued by poor design choices, shoddy construction, and chronic underfunding. Financial constraints dictated nearly every aspect of Pruitt-Igoe's construction. The federal government provided the initial capital, but maintenance had to be funded entirely by tenant rents, which were never sufficient to cover the actual cost of upkeep. To keep expenses low, the St. Louis Housing Authority and project contractors cut corners at every turn. Essential amenities like landscaping and playgrounds were eliminated from the plans. The buildings themselves were constructed with cheap materials. Doorknobs and locks broke easily. Windows were set in flimsy frames that failed to withstand the elements, and cabinets were made from thin plywood that quickly deteriorated. Plumbing and insulation were substandard, resulted in frequent leaks, flooding, and uncomfortable living conditions during St. Louis's scorching summers. Design modifications imposed by the Housing Authority further undermined the project. The original vision included green spaces and communal areas, but these features were either scaled back or removed entirely to save money. The most infamous design element was the skip-stop elevator system, which only stopped on every third floor. This forced residents to use poorly lit stairwells, which quickly became havens for crime and vandalism. Corridors and galleries were left unfinished and uninviting, lacking both security and a sense of community. Ground floor businesses and public mailboxes were also eliminated, isolating residents and depriving them of basic services. Compounding these failures was the project's racial segregation and discriminatory housing policies. Pruitt-Igoe was initially planned as two separate complexes, one for black residents, Pruitt, and one for white residents, Igoe. But as white flight accelerated and discriminatory practices persisted, the population quickly became almost exclusively black. Residents faced systemic barriers to moving elsewhere due to redlining and exclusion from other neighborhoods, trapping families in awful conditions with few alternatives. As the physical environment deteriorated, so did the social fabric of the complex. Maintenance crews became overwhelmed and demoralized as budgets shrank and vandalism increased. The feedback loop was vicious. As more units became uninhabitable, occupancy rates fell, reducing rental income and further limiting funds for repairs. By the late 1960s, vacancy rates soared, and the buildings became magnets for crime, even the Postal Service ceasing deliveries due to safety concerns. The cumulative effect of failures was a built environment that was not only physically unsustainable, but also socially corrosive. The project's rapid decline was engineered through a series of decisions that prioritized cost-cutting and speed over durability, livability, and community needs. The result was a development that, within 2 decades, went from a symbol of hope to a cautionary tale, ultimately razed to the ground while the surrounding area languished in vacancy and blight. So let's theorize on reality capture a bit. More data, less decay, right? Because what if buildings could speak? What if the concrete and steel of Pruitt-Igoe had a voice to articulate their slow deterioration, their hidden flaws, their unmet needs? In a sense, reality capture technologies offer precisely this, the ability to give physical spaces a language, to translate the silent testimony of materials into data that humans can understand and act upon. Had these digital tools existed during Pruitt-Igoe's troubled lifespan, they might have fundamentally altered the relationship between a built environment and its inhabitants. High-resolution laser scanning and photogrammetry would have captured the building's truth, not the architect's intentions or the contractor's promises, but the actual reality of what was constructed. Digital twins and BIM might have allowed planners to inhabit the building before it was built and take a stroll through the skip-stop elevator system and experience its isolation and feel the psychological weight of long, empty corridors. The beauty of IoT sensors and thermal imaging lies not just in their technical precision, but in their capacity to democratize building knowledge. Instead of problems festering in darkness, these tools could have made the building's condition transparent to residents, administrators, and policymakers alike. A leaking pipe becomes not just a maintenance issue, but a piece of evidence and a larger conversation about resource allocation and care. Perhaps most importantly, reality capture technologies could have changed the narrative itself. Rather than allowing Pruitt-Igoe to become a symbol of failure, these tools might have created a different story. One where problems were identified early, where interventions were data-driven, where the building's decline was documented and addressed rather than ignored. The technology wouldn't have solved poverty or racism, but it might have prevented a housing project from becoming a scapegoat for much larger social failures. In the end, reality capture offers something profound: the possibility of seeing clearly. And in the case of Pruitt-Igoe, clear sight might have been the difference between tragedy and transformation. Be well, recappers. Hit those show notes for some eyebrow-raising quick caps and any source you may want. We thank you for recapping and for liking and subscribing. Deuces.